Hi, in this last video, we're going to talk about machine learning. And again, we're going to really scratch the surface of the types of machine learning models that you might use. And specifically, we're going to do machine learning for text data. So the example we've been working with is data from the Scottish briefings on COVID and UK briefings on COVID. And this is a visualization we've seen earlier when we calculated the TF-IDF, which is the term frequency inverse document frequency, to compare these two types of documents, in this case, these two speeches. And we've seen that there are certain words that are more likely to appear in one and not the other, and vice versa. We've talked about things like some of the locations in Scotland where there have been outbreaks, like Aberdeen, for example, or Lanarkshire. These, never make it on the UK briefings. And also things like the word slide, where they say, next slide, please, or the word defeat, where they say, we will defeat this virus, don't tend to make it in the other one. So the fact that there are these differences in these two speeches, in the way these leaders have been talking about this issue and informing the public about it, makes us wonder, if I was to give you a sentence, could you tell me if it's more likely to come from a Scotland briefing or a UK briefing? Well, this sort of prediction is basically something that would require a predictive model or a machine learning model. At least that's one way of approaching that problem. So as an overview, what we're going to do is we're going to fit a classification model. And this will be a logistic regression, which is something we've already seen, but we're going to do something a little bit different and use regularized logistic regression, where we're using new model using lasso, which we're not going to get into the details of a lot, but this is something that's commonly used for classification problems and quite commonly used for text data as well. As usual, then we're going to do cross-validation to have a little bit of a sanity check to see, do we believe these results? Are they overfitting our data, or do they perform pretty well even on our training data when we cross-validate? And then we're going to ask ourselves the question, well, we've made some decisions along the way in terms of some of the parameters that went into this lasso selection, and also in terms of how we created our recipe for our text data preparation, and see if we can do better with hyperparameter tuning. So this is an approach where we try a bunch of parameters and we let the computer do the work, where we say, try out all of these models and tell me which ones of these are doing better. And because we're doing classification here, better would mean a higher area under the ROC curve, or a higher accuracy rate. And finally, once we have a model we're happy with, we're going to try to do prediction. And of course, this is not a perfect solution to this problem. So we're going to end with discussing some shortcomings of our implementation, which hopefully will motivate you to learn more about machine learning in future courses. So let's get to it. And I'm going to turn to the code and we'll walk through kind of these steps with the code itself. All right, so let's get started. We're going to make use of a few packages here, the tidyverse as usual, and tidymodels, and tidytext as well. We're also going to make use of another package called text recipes, which basically is very similar to the recipes package in tidymodels, but specifically contains recipes for working with text data when you're doing your pre-processing for your models. And as usual, I'm going to use the hero package to help with my file paths. So, another thing that I'm going to do here, as I've been doing in the previous videos, is set a theme for my ggplots. As I've mentioned before, that I like the minimal theme a lot. This way I don't have to add onto each one of my plots plus theme minimal. Everything that's happening in this session will basically use the minimal theme. I'm also going to set the two colors that I have for the blue from the Scottish flag and the red from the UK flag, so that we can use those for coloring things manually when we have visualizations where we're comparing the two to each other. So our data set is the speeches that we have scraped. So I have COVID speeches Scot and COVID speeches UK. So if we were to look at one of these, we basically in each row here have one of the speeches. So for the Scottish, we're going to have something like 100 and 160 of them. Yeah, 160 of them. And then for the UK, we're going to have a smaller number of them. Let's take a look real quick. It's taking a little bit of time for it to kind of pop that up because remember, we have a lot of data here. This text column is basically the entire text of the speech. So let me close that out. And let's take a look at the names in these data sets. Initially, we had slightly different fields that we had scraped from the two. So for example, for the Scottish data, I had also scraped the abstract and the title and the location as well. And then for the UK data, location wasn't there, but we have the title and the abstract. We're not going to make use of either of these things for our model. So I just decided I'm not going to worry about them. And I am using the row names to column function to add the speech ID as a column so that we can see that number throughout, both when we're pre-processing the data and also when we look at our prediction results. It might be useful to just know which speech something came from, or maybe the date will be useful as well, because if you want to go and look it up online, you probably need to know the date. So then I'm using the bind rows function to basically stack these two data sets on top of each other, and I'm also going to make the origin variable a factor. So if we were to do a glimpse here, origin is a factor, and remember that can take the value Scotland or UK, and that's what we're going to try to predict ultimately. If I give you a sentence, can the model predict whether it came from a Scotland speech or a UK speech? And this would have to be a new sentence, obviously, maybe a future speech, for example. So these are the data that we have. And the first thing that I'm going to do is to separate this into sentences. So we want to do prediction at the sentence level, not at the text level. So we don't want to feed into our model an entire text of a speech. We want to say, if I give you a sentence, can you guess for me which one, or can you calculate the probability that it belongs to a Scotland speech or a UK speech? So we are going to do unnest tokens, but here the token is sentences. So now each row of our data frame is a sentence. And if we were to take a look at the dimensions of this, so I have 17,335 sentences that I'm working with. And if we were to take a look at which ones are from Scotland and which ones are from the UK, we can see that many more of them are from Scotland. This is because we had more speeches from Scotland and because the speeches were longer on average as well. We had taken a look at the words. Chances are that means this number of sentences are higher as well. So in this case, this is something that might be an issue, and we'll address this at the end of the video when we're doing the prediction. But let's go ahead and split our data into testing and training sets. And I'm going to do something a little bit new here, which is I'm basically stratifying by origin, which means that I don't want to just take a random sample from these, but I want to take a stratified random sample from the Scotland and the UK speeches. This is important because I have this unbalanced data, so I don't accidentally end up with one of my testing set just being Scotland, for example. If the two bars were roughly the same height and we did a random sample, that would probably be good enough, but when you have this unbalance, you want to think about doing stratified sampling. So we can set our seat and split our data. And if we were to look at our split, it tells us about how much of it is basically the analysis versus the assess, meaning training, and the test, and our total sample size is what we've seen earlier with the number of sentences. And if I was to look at COVID train, this basically has the same number of columns as my data frame, but a smaller number of rows that are randomly selected. Okay. So the first thing we want to do when we're doing modeling is specify our model. We said that we're going to use a lasso, and so what that means is when we're using the logistic regression specification, we also want to set the mixture equal to 1. So that's, if it's 1, that's a lasso. If it's 0, that's a ridge regression. Neither of these are concepts we've introduced in this class, but it's important to note that these are things that you are going to learn about if you take a further course in regression, for example. So these are just slightly different regression models that we're working with. There's also a penalty, which basically controls the shrinkage of your estimates to 0. So it basically, this lasso tries to get them closer to 0 as possible. And I have, for now, kind of made up a number. Okay, so this is the penalty level that I am going to start with. The fact that I'm making that decision, and without like a super good justification around it, is something we need to keep in mind, because it's something we're going to address in a little bit in the video. And in order to fit my model, I'm going to use the GLMnet engine. So that's a different package than just using GLM. So that's my model specification. So let's take a look here. We can see the penalty with the value that I guessed. And I haven't given a great justification for. And then mixture is equal to 1, basically to say we're doing lasso regression. And our computational engine is GLMnet. The next thing is setting out our recipe. So I'm going to try to predict origin, Scotland or UK, from the sentence. So I'm not going to keep in mind the date, because ultimately I'm trying to build a model that, that might predict a future sentence. So when I'm thinking about should I include a feature in my model, there are a few questions I want to ask. Probably the first question to ask is, when you're building a machine learning model like this, is it ethical to include it? What am I trying to predict here? You may have heard in the news about things like people trying to predict somebody's sexual orientation based on attributes of their face. So that is the sort of stuff that drives people up the wall, and it should, because just because you can quantify some of these things like your facial features and put them in a matrix that will then run through a model doesn't really mean you should be building these models. So the first question you want to ask yourself is it even ethical for me to have that as a feature in my model? The next question you want to ask is, at the time of prediction, will I have this information? So when I say I want to predict for a future time, if I give you a sentence, can you predict for me which one it is more likely to be from a Scotland speech or from a UK speech? Well, date at that point becomes something you probably won't know, because we're just talking about any sentence. So that's why I didn't include date in my model. Let's take a look at some of the other names from our data. COVID speeches. So date, we don't have. Text is the full text, and we basically don't have that either at the time of prediction, because we're only doing a prediction for a sentence. URL, obviously we won't have. That's where it lives on the web. And similarly, speech ID either. So really what we want to have, and if I was to do, take a look maybe like this, is what's in my, I think this was just COVID train. In my training data, from these I really only want the sentence variable. Okay, so that's what I want to do, and the data that I'm going to build this recipe on is the training data. The first thing is basically take your sentences and tokenize it into words. Remove any stop words. That's another step that we're applying. Then also include n-grams. So in addition to doing words, should we also look at 2 words at a time or 3 words at a time? So we've talked about the concept of bigrams before, and here basically we're going to say that we want to get all of the 1 grams, which is the words, followed by all of the 2 grams, which is bigrams, and followed by all of the 3 grams. So that would be something like stay home, save. Usually they say stay home, save lives. So that would be stay home, save, for example, would be 3 words in a sequence. And then we're saying here, this is another step that we're going to use, step token filter, and I'm making up another number here. And let's keep in mind that I've kind of just set a value here without thinking about it a whole lot. This max tokens basically tells me, so this step token filter step will convert a token list to be filtered based on frequency. So what that means is, if I scroll this up a little bit more to max tokens, is an integer will only keep max tokens after filtering done by max times and min times, and it defaults to 100. I made it 400. So if a word appears more than that in the text, then we're basically saying let's ignore it and not have it as a feature in our model, not have it as a predictor in our model. And that's because if words are appearing too regularly, we might say maybe they're not going to be very predictive. So I've set that equal to 500. And that's a decision we're going to come back to in a little bit as well. And finally, we're saying calculate the TF-IDF as well and use that as a predictor too. So that's going to be my recipe. And remember that when we have a recipe step, we're basically saying that we're not yet doing anything to the data, but we're outlining these steps that at the time of fitting the model, they're actually going to be applied. Now that I have a model and a recipe, I can put these together in a workflow, and we can take a look at what this workflow looks like. It basically tells me the model that I'm going to use, a logistic regression with a particular penalty and mixture. And then we also have some preprocessor steps here as well, which are basically the steps that we outlined in our recipe. The next thing that I would do is basically fit this to create cross-validation kind of folds. So let's go ahead and do that. I'm going to do a 10-fold cross-validation this time. I have a large data set, so I can afford to have more folds. And I am, again, doing stratification by origin, just being cognizant of the fact that I have imbalance in my data. So I don't want some of my folds to end up with just Scotland data. I want to make sure that we get a good mixture of the two. So basically my folds, we can take a look at their sizes. We were working with about 13,000 sentences in our training data. So our split is something like 11.7 thousand to 1.3 thousand in the train and test within these folds. The next thing that I would do would be to basically fit these resamples. So I'm fitting the resamples to COVID folds, and I'm just going to save my predictions from that as well. I'll show you in a second why I'm doing that. This is going to be like a cooking show where I've already baked half the cake for you and I'm showing it to you because some of these take a little bit of time to run based on the complexity of our model, the complexity of the recipe steps. Some of it is a bit cumbersome to get through the tokenization or can take a little bit of time on your computer. And the third thing is that we have a large data set, so that can also take time, and we have a lot of folds and that can take time. So in order not to make you watch the video as the code is running, and also because my computer can only handle so many things happening at the same time, recording this and also running the compute, I have ran these previously for you. But again, if you would like to recreate this analysis yourself, you know the link to the repository where all of this is saved and the code is all there, so that if you would like to take your time doing it, you're welcome to do it. But I have fit this, so we can take a look at what this looks like. And we can see these are our 10 splits basically. We can collect our metrics. Let's take a look. Our accuracy is 0.856, not bad. We like it to be close to 1. Our area under the curve is 0.823, not bad. We like it to be close to 1. And I can also draw those curves, the ROC curves for my various folds. This is to check consistency between them. You know, if some of them were wildly different than others, we might be concerned about how the model is fitting various folds. But in this case, they seem to overlap somewhat nicely. Maybe one of those red ones, the fold 1. Should I maybe be concerned about that? Potentially that might be something that's looking a little bit different than the others, but overall this is looking okay, you know? And what I can do then, if I'm thinking I'm happy with these areas under the curve and I'm happy with how my folds are doing in terms of ROC, I can say, well, I'm going to just fit this to my test data. So, sorry, I can fit it to my training data to train my model. And then ultimately I can do predictions for my test data. So here I'm training the model with the workflow that I had created on my training data, now that I'm happy with it, and then doing a prediction for my testing data. So this is what my prediction looks like. For any given sentence, we're looking to see what is the predicted probability that it comes from Scotland and what really is the origin of it. I can then, based on this testing, take a look at my ROC curve and see if I'm happy with it. I can calculate the area under the curve. This is looking just like the one from the training data, which makes me happy. We're not seeing wildly different results between testing and training. And let's take a look at something. So here I have my predictions, and what I want to see is where does the model not work well? Where are places where origin actually is Scotland, but the predicted UK probability is greater than 0.05. So we can take a look at this. It's usually fun to kind of see what are the things that your model is not doing well with. Okay. So here are basically 37 sentences in my testing data where the model kind of predicted incorrectly because it gave it a higher probability for UK when the real origin was Scotland. Let's take a look at some of these sentences. We are working on this with clinicians and scientific advisors across the 4 nations of the UK. I'm grateful to all of the companies that have volunteered their vehicles and their drivers to support our NHS, and to everyone who has worked together to arrive at the solution. Let's try to see what other ones. We can see any others that maybe. So the first one I read actually had the word UK in it, and that might have something to do with this. We're more moving to questions. Indeed, I was struck this morning by a comment from the Children's Commissioner for England. So maybe this is something that Nicola Sturgeon is more likely to say, but there's the word England there. And I think we can see how that might be a word that's more likely to be uttered in the UK speeches than in the Scotland speeches. We're also, just at a quick glance, this is not an exhaustive peek through this, but not really seeing any sentences that have, for example, Scottish regions mentioned. Like there's no mention of Clyde and Lanarkshire and Aberdeen, for example, because those probably would be more likely to be attributed to Scotland. So that's kind of nice. So at this point, we could say we're done, but let's just take a stock of what we've done and see if we believe what we've done. There are a few decisions we made that we enforced on the model, and I glossed over them as I talked about them, and I really didn't give great justifications for them, which seems a little bit fishy. One of them was in the recipe step. With the token filter, I said maximum tokens should be 500. So if a word appears more than 500 times, let's not make a predictor out of it. Why 500? I have no great reason for that. It also, in the model specification for my penalty, I kind of made up a number, 0.005. I'm saying I made it up. I picked something that's in a reasonable range based on what I know about how lasso regression works. But in this case, I haven't done anything specifically about learning from the data. So some of these hyperparameters that we have are actually things we can learn from the data and we can do better with. And so that is basically called hyperparameter tuning. And the way we address this is how much you can tune at this point really depends on how much computational resources are you willing to allocate to this. What we basically can say is, can we try all possible values in the world possible of max tokens and fit all of these models and then see which one does the best? Well, that seems a little bit crazy, but maybe we can come up with a range that's reasonable for our data and then try within that range. And similarly for penalty as well. So what we're going to do in here, so I'm basically going to look at these 3 steps: specify model, build recipe, and build workflow based off of that. 3 things we've already done, but I am going to change 2 things in here, and then with those changed recipe and the model specification, we're going to build a new workflow. The first one is going to be when I'm defining my logistic regression, I'm going to say, I'm not going to make up that number 0.005. I'm going to tune it. So I'm not giving it a specific value just yet. I'm putting a placeholder there and say, we want to tune it, as in we want to try a whole bunch of things here and see which one is the best. And similarly for max tokens, we're going to say, we're going to try a whole bunch of things and see which one is the best. I've also added a min times here, where if a word appears too few times, let's just not worry about it. It was making it a little bit easier to fit the models, and that's why I did that. Okay, so with these changes in mind, I create a new workflow. So now we can see, if we take a look at our workflow, it should look very similar to what we've done before, except that we can see in our model specification that we are going to be tuning the penalty. And it doesn't necessarily show in this view that we're going to be tuning the token filter as well, but that's another thing that we're tuning. So tuning meaning that we're going to try a whole bunch of values for them. When I say a whole bunch of values, obviously we need to put some limits as to how many things we're going to try, or we would be running these models for ages. So when you think, if you ever hear people saying, oh, my models take a whole lot of time to run, one of the reasons might be this, that the tuning stage might take a bunch of time, especially if they're trying out a bunch of values. So we're going to create a grid. And let's take a look at this grid. In fact, it's slightly big, so I'm going to pop it open in the viewer. And you can see here that what we have are a bunch of penalty values and a bunch of maximum tokens. And you can see that some of these are repeated. So these various penalty values, there are 5 different penalty values that we want to try out. And we're going to try them out with maximum tokens equals to 500 first, and then with 875, and then with 1250, and then with 1625, and then with 2000. So that makes 25 different model specifications, each of them to be applied to go through a 10-fold cross-validation. So that's 250 models that we're going to need to fit. And this is the reason why I am taking the cooking show approach here and saying, well, I've already done this prior to starting to record this video, because that really does take a long time to run through. And when I say a long time, I don't mean an hour, but definitely more than just 10 minutes. Before I do that, I set a seed again, and I did actually run this cross-validation. But let me, even though I'm not going to run it for you because we're using a new function, I'd like to show you what we're doing. We're using a new function called tune grid here. So on this grid, basically do the tuning. We give it a workflow, just like we've done before. We mention what our resamples are, like we've done before, but this time we also give it a grid. Okay, and then say, let's save the predictions so we can take a look at them. So in order not to accidentally run this and put into motion something we didn't intend, I'm going to close that out. And so let's take a look at here are all the various metrics, and you can see that there's a lot here. Because we're taking a look at, so there are 50 rows in this output. We're taking a look at accuracy and ROC for each one of these 25 combinations. We can take a look at the plot for these. Sometimes it gives this error. There we go. So we can basically see here on the, what we're seeing here is on the, let's take a look. So on the x-axis, we have the amount of regularization. So that's the penalty values that we tried, the 5 different penalty values. And on the y-axis, we have either the accuracy or the ROC. These are numbers we want to be high. And then the different colors represent the different retained tokens. So for accuracy, if you look, the purple one manages to hit a pretty high accuracy level. And the purple one also, it seems like, stays pretty high for ROC as well, versus the red one, which is with 500 retained tokens, is not doing very well, which, if you remember, is what I had tried before. So clearly the specification I had before with only 500 maximum tokens probably not doing a good job, right? So I might choose a different number. And this is why it's important to think about what are some random decisions I imposed on my model, and is there a way I can do better on them? Sometimes the answer to that solution is mathematical, and sometimes the answer to that solution is best achieved by simulation, as in you try out a bunch of things and grab the one that works the best. So there's another function that we can use called show best, So these are the best values in terms of the ROC, and that's what I want to do my selection based off of. And basically what I'm going to say is these are the best choices for penalty and maximum tokens. So instead of 0.005, it should be 0.001, and instead of 500, it should be 2000. That's basically what I want for my model. We can also take a look to see the ROC curves for each one of these folds, and we can see that the bend is nicer here. They're all higher, and between the folds, no big differences. So that's also nice to see as well. Scroll this up a little bit. And what I then want to do is say finalize things. So this is something I want to keep a record of. So my final workflow should not say tune anymore here for penalty. It should actually tell me what that number is. Another thing that we might want to think about at this point is, well, which predictors are useful, right? So far we've said, fine, this model works well. ROC values are higher, but so what? Even if it does work well, sometimes what we're really interested in is like, what is actually happening under the hood? What predictors did we end up using? I mean, we have these almost magical recipe steps that tokenize things and use some n-grams and whatnot, but which one of them actually are we using, and or which one of them are actually important for predicting or classifying between Scotland and UK in this case? And so for that, we use a measure called variable importance. So how do we do this? Oh, another thing I should mention, I think that we did, we kind of mentioned this before, but I want to take a note of these ROC, area under the curve values, 0.885, which is better than what we saw earlier when we didn't do the tuning. We scroll up and take a look at, so this was prior to tuning, we were getting at 0.828, and now we're able to get to 885. So that's why we're preferring the tuned model to our original one where I kind of made up the numbers. So that's important to keep in mind. And what we want to talk through now is this variable importance thing. So we have a final workflow, and we want to then fit it to our training data, and then just basically pull out the fit. And then we're going to calculate the variable importance for each one of the variables. So we have lots of predictors in our model. A lot of them are words or bigrams or trigrams. And then we basically want to take a look at which ones end up having the highest variable importance. This bit also takes a little bit of time to run, so I created that ahead of time. Let me go ahead and show you the visualization, and then we can go back to the code and see how that code translates to this visualization. So here we go. We have on the x-axis the variable importance, and on the y-axis various predictors or features from our model. So what this is telling me is that the word slide, for example, is highly predictive of a text being from the UK, a sentence being from the UK. And perhaps we're not so surprised about that, because we've seen this in the TF-IDF before as well. Another one we had talked about when we looked at the TF-IDF was defeat. We had said that that's a word that seems to more likely occur in the UK data as opposed to the Scotland data. And again, we're seeing that as an important predictor show up here. That being said, this picture is not the same picture as the TF-IDF picture to begin with. So when we just did exploration on our data without fitting the model, we were able to identify the different features, some of which actually do show up here, but we didn't get to do when we just looked at those was to see the effect of bigrams or trigrams, and we could have actually added other predictors to this as well. For example, we could have counted how many numbers are uttered in a word, because I think based on just watching these speeches, it might be that the Scottish speech tends to be a little bit more heavy on the numbers that are getting mentioned than the UK speeches. This might just be a hypothesis that's wrong, but we could have evaluated this hypothesis. So the modeling allows us to move beyond the exploration, but it is nice to see that the model results actually line up with our exploration as well. And similarly on the Scotland side, the change sense, that is probably a change in sense of smell or taste. That is something Nicola Sturgeon mentions a lot in terms of if you have this symptom, stay home or call NHS, get tested. Glasgow, Lanarkshire, these are areas that get mentioned a lot in the speeches in Scotland and are not predictive of a speech being from the UK, but more of Scotland, and that's why we're seeing them here. Let's take another look. If I scroll down a little bit here on this list, physical distancing is another important variable that came up in Scotland. And perhaps that's not unexpected, because we had seen that earlier in our exploration, the Scotland speeches use physical distancing as a term, but the UK speeches keep using social distancing. And it doesn't actually show up on the UK side as important, and that's probably because the Scotland speeches also did use social distancing as well. So it might be hard to tell if the term social distancing is used. It may not be so predictive of it being from the UK. It could have been from Scotland as well, but the term physical distancing actually is predictive because it was, I think, never used in the UK. So this is basically a way of starting to think about which variables are important. If you have other regression experience prior to this course, you might know of p-values as a way of kind of determining which predictors are statistically significant. This is in a way, this is a much different approach of kind of evaluating importance of variables without tagging on that heavily loaded term, statistical significance, but kind of getting at a similar idea of informing us about what in our model is most predictive. So in order to create this, we've basically taken the importance values and taken their absolute values, because we're basically not so interested in if it goes one direction or another, but just interested in, is it useful to begin with? And then we've basically said any importance that's not 0 is something we want to keep in mind, and then we want to group by the sign of that importance. So is it positive or negative? Because in this case, positive would be predicting Scotland and negative would be predicting UK, just based on how we had our positive would be predicting UK and negative would be predicting Scotland. I guess they're in alphabetical order in this case, and that's the reason why. So that's how we've created this visualization. And ultimately what we might do is, if we are happy with this, we might fit this. Oh, I most certainly should not have done that. We can fit this to our final model. And we can see that our testing data, we can see that with our testing data, our ROC is 0.887, which is higher than what we had without the tuning, and similar to what we got from the training data with the cross-validation. And our ROC curve is, looking nice as well, with a nice bend in it. So all of these are to say we were able to fit a predictive model for predicting which country a sentence comes from. Now, the next step here might be, what if I gave you a new sentence and just from out of the blue, can we predict whether it's more likely to be from Scotland or the UK? And we absolutely can do that with this model. The one caveat that I want to come back to is something that we have talked about at the very, very beginning as a potential issue, which is this, which is where we looked at the distribution between Scotland and UK in terms of the number of observations. We mentioned that this is an unbalanced sample. We have more data from Scotland than UK. So when I give the model a sentence to say, predict for me, I'm not actually saying that, most likely, what I want is not to say that I know there are more sentences from Scottish speeches out in the ether, so any given sentence is more likely to be from Scotland anyway. What we are saying is, what we would prefer to say is, don't worry about the fact that there have been more speeches so far from Scotland than from UK, but just given the linguistic characteristics of the sentence, can you classify it as one or the other? In that case, this unbalanced sample would actually create a problem. So what really we should have done, or not necessarily really what we should have done, but at least consider doing, is should we have downsampled the Scotland data to begin with when we create our training and testing splits, so that our model is not just like overwhelmed by the Scotland data, because the fact that there are more observations from Scotland is not actually informative about the linguistic features. It's informative about what happened in the past, but when we're thinking about doing a prediction for a future sentence, that's not something that we actually care about, that there have been more speeches from Scotland. We just care about, given the sentence's linguistic features, can we classify it as one or the other? We're not going to go back and fit that model with the downsampling one more time, but if you are studying more machine learning, that's definitely something that'll come up. So if you're interested in these sorts of approaches, I strongly recommend taking a second course in statistics, where you learn more about modeling, where, for example, we've thrown around this word lasso a few times today, and that's going to be a useful model to learn about. And then take further machine learning courses where you can learn more about building these predictive models and tuning them, and then ultimately doing these predictions as well.